It's really a pleasure to be here and visit your institute. So I will be talking about unstable neutrinos. So okay. So this talk is based on two of our works performed with my collaborators. And just to give you a basic idea, what we did was we did the neutrino propagation in matter when the neutrinos are decaying. Now, neutrino propagation in matter is a very, it is a very easy, at least for, we did this paper for 2 generations. And for 2 generations, matter propagation is really easy, and we do it at the very beginning of our, sometimes in MSc also, like during our beginning studies, but we showed that how when there is a decaying component, then what happens, even in the 2 generation picture, it's not very easy. And then we did an analytic treatment of 3 flavor neutrino oscillation and decaying matter, and we gave some compact formulations for the probabilities. So just to start, that it is found in several experiments that neutrinos can change flavor after passing through a distance. So if we start with some flavor, say mu mu, then at the detector, we can detect some flavor mu tau. And this is possible if neutrinos have mass and mixing, and the conversion probability is oscillatory. And this is the phenomenon of neutrino oscillations. And this requires neutrinos to have mass and mixing. And in the standard model, as we know, neutrinos have no mass. So neutrino oscillation was the first signature of the physics beyond the standard model. Now, we had oscillation evidences from several experiments involving the solar neutrinos, atmospheric neutrinos, reactor neutrinos, and accelerator neutrinos. And together, sorry, there is some rearrangement. Together, they established the 3 flavor paradigm of the neutrino oscillations well, and we know that there are this is well established, and these are governed by the 2 mass square differences, delta m squared 2 1, which governs the solar oscillations, and delta m squared 3 1, which governs the atmospheric oscillations and can be also probed in reactor experiments. And we have 3 mixing angles, theta 1 2, theta 1 3, and theta 2 3. And their values are now quite well measured, like theta 1 2, theta 1 3, and these parameters are very well measured. There are some unknown parameters which are not so well measured yet. But to come back to this neutrino oscillation, so neutrino oscillation occurs when the mass flavor eigenstates, which are the states which are produced in weak interaction decays, are linear combination of the mass eigenstates. And this U is the mixing matrix which I showed earlier. And what happens here is that these mass states propagate, evolve in the with energy to the IEIT, and then we can calculate the probability. If we calculate the probability of a flavor nu alpha going to a nu beta, then we can find that this is given by this factor. And if the neutrino masses are different of the different states, then this factor is non-zero, and then we have a non-zero conversion probability. And for 2 flavors, this U takes a simple form parameterized by 1 mixing angle. And then we have supposing we consider nu mu oscillation probability, then it is given by this mixing angle which denotes the amplitude, and this term which which depends on the mass square difference of these 2 states. And this is kind of the oscillatory of the phase term. However, there is another way of calculating the oscillation probability which we are going to use, which is that you write the equation in the mass eigen basis, the propagation equation, and then the probability can be just the time evolution of this operator e to the I HMT times in both sides we multiply by u to get from the mass basis to the flavor basis. And this is the formulation which we are going to use. And as I said, the three flavor oscillations are well established and we have certain parameters measured well. However, oscillation is the leading solution to the observed anomalies, and there can be new physics effects at a subleading level, which the oscillation data, which the data has not yet ruled out. And there are many new physics effects which are considered like sterile neutrinos, non-standard neutrino interaction, long-range force, violation of fundamental symmetries, etc. And one of them is the neutrino decay, which is the subject matter of the talk today. So what happens is whenever we have any of these new physics scenarios, there is a change in the oscillation probability. So oscillation probability becomes different. So that is one thing to study. What is the oscillation probability in place of these new physics? And then one can constrain the new physics parameters. Also, one can study that because of this new physics, whether how the known parameters in any way determination of the known parameters are affected. These are more relevant for parameters like the CP phase, which we do not know yet. And if we have a new physics, then we can have a new source of CP violation, and that can complicate the determination of the original CP phase. So we consider neutrinos decay, and how neutrino can decay in two ways. One is that neutrinos decays to sterile state. So there is some right-handed neutrino and some some scalar, singlet scalar. So neutrinos decays to completely sterile states. This is called the invisible decay, and there is visible decay when neutrino decays to active state. For instance, the neutrino can go to another lighter neutrino and say, for instance, a myron. So different these two types of decays have been considered in the literature. So what happens is that these were considered first as solution to the disappearance of the solar neutrinos long time back. However, later the data disfavored the neutrino decay as the leading solution to the solar neutrino problem. Now, neutrino decay manifests as this term, exponential minus mi L tau I by E. Mi is the mass of the neutrino state and tau I is the lifetime, L is the distance traveled, and E is the energy. So, as I said, that neutrino decay cannot be the solution to the solar and atmospheric neutrino anomalies by only solution. Dominant oscillation plus decay as subleading solution is still allowed, and one can get constraints on the lifetime. So like, this fraction of neutrinos decaying, if we see, then this is this exponential minus alpha L by E. When this factor is 1, then we have no decay. And when this factor is like very small, then like this is 1, and then we have complete decay. So it will depend on your L by E, that how much of this decay constant one can probe. So that is the important factor here. And there are bounds on this factor from different experiments, and these bounds for these experiments have different L by E, and so they have sort of different, but these are all like from Minos and atmospheric from long baseline. So because atmospheric has a greater length scale, so it can go up to a higher number, or for as far as the decay constant alpha is considered lower. Now, for all these studies, the analytic expressions of probabilities in presence of decay are calculated in vacuum. But we know that the matter effects are important for neutrino oscillations. So if we consider the simple oscillation picture, then what happens is in vacuum, I have a Hamiltonian, and in matter, I have a potential due to the interaction of the neutrinos with the electrons in the matter. So the mass eigen, the vacuum eigenstate goes to matter mass eigenstates, which we denote by M. And then what one has to do is one has to solve this equation in matter, calculate the eigenvalues, and then one has to calculate the probability in matter. So this cartoon says this, that I have nu e and nu mu, and this nu1, nu2 are the states, mass eigenstates in vacuum, and nu1m and nu2m are the mass eigenstates in matter, and these are rotated by theta m from the flavor states. So one has to diagonalize the effective Hamiltonian in matter and find the eigenvalues and the eigenvector. So if we write the two-generation propagation equation, then the matter Hamiltonian is this, my vacuum Hamiltonian, plus the potential term. So this is in the flavor basis. So I have given a rotation u dagger to the mass basis. And then this is the interaction potential, which is denoted as 2 root 2 GF NE. NE is the matter density, this part. NE is the electron density and E is the energy. So what happens is that one method is that we diagonalize this and find the eigenvalues in matter, and we find the effective mixing angle in matter. And what happens here, we see that if delta m square cos 2 theta is equal to 2 root 2 GF NE, then the theta m goes to pi by 4, which is the famous MSW resonance, and one can calculate the, for matter of constant density, the two-generation probability will be the same, but the mixing angle will be expressed by the matter mixing angle, and the mass square difference will be expressed by the mass square difference in matter. And another way of calculating this is that we find the matter mixing angle, we exponentiate this Hamiltonian, and then we find the P alpha beta. Now, what happens if the neutrinos are unstable? So the thing is that, this is an example of unstable R, so this is the red cube at Broadway, New York, which is like this is as a diagonal. And if in the context of financial market, this signifies chance, like the rolling of dice. And it was written about this, that a work that is unbalanced appears unstable, creates tension, and makes the viewer uneasy. And here the architecture is that all the lines are diagonals. So that is the thing. And in this context, what happened was, when we were doing these works on decay, we had some numerical studies for atmospheric neutrinos, and we found that there are no analytic expressions available, and it was creating some tension in problem in finding the the physics behind it. And so then we thought that, okay, that was our motivation of trying to solve this problem in matter. So the problem here, what we faced was that in presence of decay, the Hamiltonian is non-Hermitian. So now this is the first thing. And another thing is that the decay eigenstates and mass eigenstates need not be the same. So this H and gamma may not commute. So then they are not simultaneously diagonalizable by unitary transformations. However, one can use non-unitary transformations to diagonalize this, and in this paper, it was done in vacuum, the diagonalization by a non-unitary transformation to calculate the probabilities of neutrino in presence of neutrino decay in vacuum when the off-diagonal terms are present. So now what we noticed is that even if the decay eigenstates and mass eigenstates are same in vacuum, matter effects make this mismatch inevitable. So the decay eigenstates and the mass eigenstates in presence of matter are not the same. I will show that. But first, if we assume that they may not be the same, then what we do is that we write a general Hamiltonian in matter, where we have the decay term. This is the A1, A2 are the, so this is in a basis where the Hermitian part is diagonal and the non-Hermitian part is there. So we go to the basis such that the Hermitian part is diagonal. Then the flavor revolution is given as this e to the minus I HMT mu 0. But because HM and gamma m, this commutator is non-zero, we cannot write it like this, that e to the minus I HMT, because as I showed you earlier, the way we are calculating the probabilities, we are multiplying u e to the minus I HMT u mod square. That's how we are calculating the probability. But if this is not commuting, then we cannot write it, and then what one has to do is that one has to express this as a chain of commutators using the what is known as the Zassenhaus formula, which is the inverse of the Baker-Campbell-Hausdorff formula. So this is the formalism that we take this matrix, and this is in the basis where the, so in our language, it is in the basis where the matter mass, in the matter mass basis. So this part, Hermitian, the matter mass part is diagonal. And then we take these off-diagonal components also and the complex decay terms also. And then we do some redefinition. So this is basically like we define a quantity di, ai minus ibi, then delta a, a2 minus a1, delta b, b2 minus b1, and delta d is d2 minus d1. Now all this is done in order to express this Hamiltonian in terms of traceless and identity. This is what we do for the simple two-generation neutrino oscillation case also, that we, because if we calculate the probability, you know, e to the minus I HMT, so the part that is proportional to identity does not contribute. And then we have taken out the trace and we have written it in terms of two, reformulated in terms of two matrices X and Y. And the commutator of X and Y is, we can see, is non-zero.
Just a second. So what D2 are D2 minus D2 there. So delta D is coming from.
So DI is AI minus IBI. And
DI
then
is AI minus.
delta D is A2 minus. So then it is just like rewriting this whole thing to take out the identity matrix and express it in terms of two traceless matrices.
And just to make sure, at this stage, still your matter potential is Hermitian.
See, I will show later when I write the matter potential, how is it here. I am not writing anything, but what I am saying is that I have HM minus I gamma m by 2, and this is the basis where HM is diagonal. So the idea is that, you know, when we are doing the two-flavor analysis without decay, we have diagonalized the matter part. So in presence of decay, let us use those bases, but because this is not commuting with the Hamiltonian in that basis, we are using the Zassenhaus formula to express the e to the minus I HMT and getting an expression for the probability. So the inverse Baker-Campbell-Hausdorff or Zassenhaus expansion is an expansion similar to the Baker-Campbell, and it is expressed in terms of commutator. And so in our case, we have this kind of identifications. But the main thing here that we used was, we found one paper where they have given this expansion in terms of a summation in terms of an infinite series, and where this Lx is the symbol for the commutator, Lxy is commutator xy. And so we can write this yn as y by n factorial, n minus 1. So this is from this series, how this series is expressed. And then we thought that if we use this series, then we can use our Hamiltonian and we express orders up to gamma bar. And gamma bar was a parameter related to the off-diagonal gamma by delta D. And then we can express this e to the x plus y in terms of this factor. Okay, so this is just using this series and consider this p up to 1 and then truncating this series and then getting expression for e to the x plus y. So then what happens is that if we do that, and then we can calculate the amplitude for the in the mass basis in matter amplitude matrix in terms of a 2x2 matrix, again in terms of these parameters. But what is important is that now what we can do is we can use this e to the IHMT, and to calculate the flavor amplitude, we have to multiply by the mixing angle, and then the probability is mod n square, mod a square, and then we can find some expansion in terms of some expressions in terms of the parameters. And so this is what finally it comes to, that this was our matrix. We used the Zassenhaus expansion and we get some compact form for the survival and the conversion probabilities. So this is a lot of mathematics, but it's very easy, like because it's just a 2x2 matrix. So once we use the Zassenhaus thing, it's not difficult. So it gives us some kind of physical insights. For instance, we can see that if we consider normal two flavor oscillation, we have P alpha alpha equal to P beta beta and P alpha beta equal to P beta alpha. But here that is not taking place. For instance, if you can see here, then you know this is my A alpha alpha, A alpha beta, A beta alpha, A beta beta. And you see that A chi going to minus A chi is relating my A alpha alpha and A beta beta. And here I have chi going to minus chi for P alpha beta and P beta alpha. So that is the thing that, you know, in even if you have a two general matrix, then these scenarios are changing. Now we also expressed this. So this was up to order gamma. So that we have truncated the series. Then we also did consider the next higher term. And then what we did was we plotted this to see the accuracy of the expression. So this green curve is for no decay. And then this cyan curve is exact with decay. And then this blue is showing that if we ignore this commutator. So that is the thing that we can see, that if we ignore the commutator, then we will not get the result which is matching with the exact result. So now for doing this plot, we took some arbitrary parameters because this matrix is in the mass basis in matter. So this is not really a realistic scenario, but you can see that what we see is that if we consider this delta p mu mu analytic minus exact, then we can see that if we ignore the commutators, then our error is much higher. If we take up to order gamma bar, then we get error in this range, like for some energies it's very low, but some energies it's high. And if we go to the next higher order, then the error is even less. But the more realistic is the 3-generation scenario, which I will discuss. But before that, I wanted to map it with the usual scenario that we know and show you exactly what is happening. Now, if we have the Hamiltonian in vacuum with mass and decay states same, then we have this off-diagonal terms as 0. And we have m1 square minus I alpha 1, m2 square minus I alpha 2. So we have both the neutrino states decaying to invisible states we are assuming. Now, when we go to in matter of constant density, then this mass basis is rotated by u dagger. This is the matter potential. This is in the mass. This is in the flavor basis. So this is in the flavor basis. So then we have it as this neutrino electron scattering potential plus the decay term. This is also rotated by u dagger. Now this first two terms is my usual two flavor mass matrix in matter, which I write in this way, delta. So it comes, and then from there we get that usual form of tan 2 theta m, which I have shown, and we can diagonalize this and we get m1 square 0, 0 m2 square, right? So this is my usual, this part is my usual matter treatment in two flavor. But here I also have a decay part along with it. So then what happens is I have to get the decay matrix in the matter mass basis. So first I had a u dagger rotation, and then I go to the matter mass basis. So I have a um dagger rotation. So this is my decay matrix in matter, and you see that the off-diagonal terms are generated in matter. So I started with a matrix which did not have off-diagonal term in vacuum, but just when I come to matter, then in the matter mass basis, I will have off-diagonal terms in matter. So that means that the decay basis and the matter mass basis are not the same. And here we can compare now with our general form that we had, and we can see that my A1, A2 are my matter mass eigenstates, and my B1 and B2 we can identify from here the complex part, and this gamma we have, and for the simple 2 cross 2 trace actually we have chi as 0. So we have this gamma. So we have identified our general case with the parameters with this case which we already know very well. And this with this mapping, we can use the general formula and calculate the probabilities. So this is to be noted that we are using the matter basis. This A1, A2 is in a basis where these matter mass eigenvalues are there. So that is diagonal. And then the decay has developed some of diagonal component, the decay matrix. Now, if we consider a single decay neutrino, say we take alpha 1 as 0, because normally we consider that, then these are my eigenvalues, but you can see that I have B1, B2, and gamma. So I have B1 and B2. So I start with a single decaying neutrino, but both eigenstates can decay in matter. So these are the kind of physical insights that we got from these kind of analytic expressions, which actually I did a lot of work on numerically on decay, but we did not realize this, that that both states can decay in matter. These things were not very clear. Now I use the general expression which I showed. I put this A1, B1, B2, etc., and I get this kind of a closed expression. This is the expression for single decaying neutrino in the two generation case in matter. And here the beauty of this procedure is that I can use this theta m is my matter mass eigen mixing angle in matter, which my usual MSW angle. So I can use that usual MSW angle, etc., and I can express. And if I take the no decay limit, it is giving me the usual two flavor probability in matter of constant density. So another thing that we realized was that, so I used the Zassenhaus expansion, but another way is to use a matrix, properties of the matrix exponential, and any 2 cross 2 complex matrix can be exponentiated like this, which is nothing but the same as what we do for the expressing in terms of the sigma matrices. And then also we can calculate the probability in the 2 cross 2 case. And then what happens is that this is exact, because here we don't have to do any Zassenhaus or anything. Here I am just exponentiating. So when I said exact, we also used this formulation and we compared our results with this and the numerical values, and this and numerical values matched very well up to machine accuracy. And but this is for 2 generation it's possible, for 3 generation this is not possible. So when we go to 3 generation, then we have to again take some approximate methods. So I will come to the 3 generation. Before that, if you have any questions on this part, then we can discuss. So it may be little algebra. So I don't know, it may not be very easy to get it during a talk, but the main thing that I want to tell is that what we used was, we used the matter mass basis and we calculated the probability in the matter mass basis using the decay matrix in terms of an expansion, and then we got some approximate probabilities in presence of matter. Then we also gave an exact thing, and this was the thing that this is the most for understanding that part. This what happens in for the usual 2 generation case, that is the important identification, that these terms are generated in the matter mass basis, which shows that the decay eigenstates and the mass eigenstates in matter are different. So then we did the 3 flavor case, we did various approximations. One is the 1 mass scale dominance approximation and decay of nu3. Here we used the 2 generations Asenos results. Then we use a 3 generations Asenos, which I am not showing here. Then we did probabilities expanded in terms of various small parameters. And here we used the Cayley-Hamilton theorem. But I will just give a little bit of the results to show you the thing. Now the thing is that in the 3 generation case anyway, even if there is no decay, it's very difficult to solve the propagation equation in matter analytically because we have a cubic equation. So there are various approximations which are any case adopted. So one of them is the 1 mass scale dominance approximation, which is valid because if I have considered the delta m squared 3,1 and alpha is my delta m squared 2,1 by delta m squared 3,1, then alpha is a small parameter. So my delta m squared 2,1 is 10 to the minus 5 EB squared and delta m squared 3,1 is 10 to the minus 3 EB squared. So we neglect the delta m squared 2,1 term. So this is the 1 mass scale dominance approximation. So what we have is with the usual term, we have a decay of the nu3. So we write a gamma 3 and we take this alpha tending to 0, then I have this equation. Okay. Now what happens is that in the usual, and my U is R23, R13, R12 in terms of the rotation matrices. Actually the CP phase drops out because when we have the delta 2,1 as 0, then and mathematically you can show, but just to understand physically, when I have delta 2,1 is 0, then actually I have 2 massive states. So then the CP violation is not possible with 2 states, right? So then the CP phase, actually you can show by doing the mathematics that the CP phase drops out. Also, what happens is that this R12, because I have delta 2,1 as 0, I can give the R12 rotation here, and so then because the 2,1 mass is 0, so this angle can also be dropped, and then we go to a basis which is a 3-2 rotated basis, and we have just R13 and R13 dagger. So the thing is that in the 1 mass scale dominance approximation, the whole thing becomes a 1-3 resonance. So it's like a 2-flavor resonance, but in the 1-3 sector. But here we also have the decay term. So what we did was that exactly the way we have done in the 3 generation without decay case, we diagonalize the mass part, the mass in the mass basis, and then we have the decay part in that same basis. And then if we write that, then we can see that we can get this off diagonal terms which gets generated, and this gamma 1m also gets generated. So basically it's this 1, 3, 2 cross 2 block, and the physics is exactly the same. And then we can express this in terms of these parameters just as before. So the diagonal and off diagonal terms are generated here also. And then we can calculate following the same method and remembering to give my proper rotations, because I had a 2-3 rotation first and then this matter rotation to my decay matrix. Then I can find the expression for the probability in 3 generation in the 1 mass scale dominance limit. And I can show how the results match with, like, this is the 1300 kilometer, which is the due baseline for decay. So this red is the exact probability, and then this blue is the OMSD, and then this black is that if we do some expansion in S13 alpha, which I have not shown now, but it's there. And we can see that this is for 7,000 kilometer, and this is the exact term, and then this blue is the OMSD. So this is the kind of accuracy that we are getting for the this OMSD. OMSD in any way is, even for the 3 generation without decay, is an approximation which is more valid for 7,000 kilometer. You can see here the error is large, but here the error is smaller for the 7,000 kilometer. So then we also, so then we considered first the nu3 decay. We also considered the general decay matrix, assuming all to be decaying and all the off-diagonal terms. Now, since decay is a subletting effect, there are length scale associated with decay should be less than that of oscillation. And with that, we can find some constraints on these gamma ij parameters, assuming that decay is a subletting effect. And finally, what we can show is that for the current scenarios, like for the long baseline and the atmospheric experiment, we can show that the gamma 1, gamma 2 is of the order lambda cube, and lambda is our small parameter, which is of the order of sine theta 1, 3, and gamma 1, 2 is of the order lambda cube, but gamma 1, 3, 2, 3 is of lambda square. So these are the various orders of these various gammas from the current mass square differences available. And then what we did was we applied the Kelly-Hamilton theorem, which gives us a way of expressing the probabilities in terms of the differences in the eigenvalue. So this is the general formula for the Kelly-Hamilton matrix. So any function can be expressed in terms of its eigenvalues. But for the three generation case, calculating these eigenvalues also needs some approximation. So one mass scale dominance is one approximation, and another approximation which is often used is to provide expressed in alpha, which is delta 2 1 by delta 3 1, S1 3, which is the mixing angle, theta 1 3, which is small, and gamma 3 and gamma ij. These are the small parameters that I showed we have. And to give you an idea again of these small parameters, alpha is of order lambda square, and S13 is of order lambda, and then my gamma 1323 lambda square, and my gamma 3 is of the order lambda. So we don't take the lambda cube terms, but we took the other terms. And then I have this P alpha beta as P alpha beta, which is without decay, plus gamma 3, plus I take the gamma, the off diagonal terms. And what I can see here is this is the P mu mu. So if you consider this first part, then it matches with the similar expressions in alpha S13 limit given without decay. Plus we get a term in presence of decay which goes as gamma 3 and gamma 3 square, and then if we take this, then we get some terms with gamma 1 3, gamma 2 3. And if we consider PE mu, then also this term is the same as what we get for no decay. Then we get a component of decay which is of gamma 3, and then we have another term which is this gamma 2 3 and gamma 1 3. But here one thing we can see is that here in the decay part, matter dependence is not coming. All are vacuum expressions, and this A is my matter potential. But here in PE mu, the matter term is there, plus the off diagonal decay terms are like S1 3. So they are of the same order as gamma 3. So then this is a region in the LE plane where we have compared the delta P alpha beta numeric exact minus analytic is less than 1 square. So the WMSD approximation is like in blue. This is P mu mu. This is with decay and this is without decay. And this red is the expansion in alpha S13 gamma 3. And in the purple is the region where both approximations satisfy this condition. And in the gray regions, these analytic expressions are not valid. So then we find that in a large region in the L and E plane, this value delta P alpha beta less than 1% is valid for OMSD as well as the alpha S13 gamma 3 expansion. So, some of the interesting things that can be found from these expressions is that, one thing that we found is that if we consider a minima of the survival probability, P mu mu, then usually we think that in decay there is a reduction in the probability, but that is a reduction in the conversion probability. What we can see is that in presence of decay, there is a rise in the survival probability at the minimum of the survival probability, which we call the SP mean, survival probability minimum. And if we take gamma 3 and 0.1, then we can get, so this is the numerical without decay and this is the with decay. So we can see that we can get some kind of a rise, like this is 0.03 at the first oscillation maxima and this is like 0.1 at the second oscillation maxima. And this can be expressed from the expressions that I showed you, that P mu mu at the dip and the first dip and second dip, we can find these expansions and we can express this. And the second dip is like where we have this 0.1, this is given by E nu L by 1000. So these are like the second oscillation maxima. And this is observable in these experiments like ESS, nu SB, T2HKK, etc. In fact, then I realized that before this paper, we wrote one paper where we had experienced, we had observed this, that, you know, if we have 1100 kilometer baseline, right, which is the T2HKK baseline, then in presence of decay, we can see some rise. And we have shown that, you know, this, because of this rise, we can get an enhanced octane sensitivity in presence of decay. So this we had shown in this paper, which was before that, but with our paper, we got some analytic explanation of this result, which we obtained earlier. So there are many future possibilities which one can do, which we have been planning, but we have started some, but not done all of them. One is that calculation of probabilities in varying density, which can be relevant for sun or supernova in presence of decay, because we have done for constant density. Then one can study the implications at a phenomenological level. I have shown you how the octane sensitivity can be enhanced in presence of decay in a second oscillation maximum baseline. There are degeneracies in presence of oscillation, whether in presence of decay there is any impact on that, especially the decay and the theta 2 3, both they have a correlation, because theta 2 3 the sine square 2 theta 2 3, they denotes the amplitude, and decay can also affect the amplitude. So whether there something is possible, then you know, we are also considering that in other, if we have other new physics, like there are after our paper came, there was one study using NSI and one study using the for the Majorana phases, etc. Then also the density matrix approach has been studied for decay or things like that. But if we have a dissipation, then the Lindbergh equations are used, and we were thinking that if one can do some things using these equations also. So I started with a fable, and so the moral of the fable is this, that we should not undermine 2 cross 2 complex matrices. That's what we realized. Thank you.
Any questions?
I had a question. I might have misunderstood, but could you explain the difference between the two? So there is one mass scale dominant case that you've considered, and then you've also considered an alpha expansion in terms of alpha S13. And so will the expansion in alpha come after the OMST?
So, you know, the expansion in alpha means, OMST means alpha is 0.
Right.
But OMST means alpha is 0, but I did not take any expansion in theta 1, 3. So OMST means alpha is 0, but theta 1, 3 is exact. And alpha S1, 3 is means alpha also we take, and we take S1, 3 also. And then we also take alpha S1, 3 terms, because these are all same order, alpha S1, 3 and alpha S1, 3. S1, 3 square actually comes there. So the thing is that, you know, they have different regions of validity. If we consider, for instance, Dune baseline, then we don't get the resonance phenomena there. So for Dune baseline, alpha S13 expansion is good, because we should not neglect alpha. But if we consider, say, atmospheric neutrinos, for which the 7,000 kilometer baseline is better, then the 7,000 kilometer baseline, we have the matter resonance. So I have a resonance condition. I show delta m square cos 2 theta 2 root 2 GFNE. If we consider the GeV energy neutrinos, and if we consider 7,000 kilometer baselines, then the resonance condition is satisfied. And resonance is is in three flavor case, the resonance is the enhancement of the 1-3 mixing angle. So there the OMSD approximation is better because the 1-3 is drives the resonance, and if we assume 1-3 as small, then it doesn't work so well here. That is in general in presence absence of decay also. So which expansion is valid, you should take, that will depend on your baseline and energy. So for instance, like for instance, I am showing here that these regions, here the blue is giving better than the red. So you can, if you see the baseline and energies, then you can see that for higher baselines and for, energies like close to resonance energy, so which is like, maybe here, then the OMSD is a better approximation. So which expansion we should use depends on which baseline and energies we are considering. So OMSD is they both are used, but for atmospheric neutrinos, OMSD is better, and for the long baseline neutrinos like Dune, then the alpha S13 works better. The OMSD, the alpha 0 problem is that, the CP effect is also gone. But if we have the alpha S13, then the CP effect is there. And so when we want to probe the CP, then this is better. But atmospheric neutrinos, at least the muon channel, the high energy atmospheric neutrinos, they do not have so much sensitivity to CP. But if we consider low energy, then we have to see which expansion works better where.
Just a question.
Please.
So when you're doing the expansion in terms of alpha and S13, how do you exactly calculate the I might have missed it. How do you calculate the analytical expression?
So the thing is that you have to use this Cayley-Hamilton method. So you have to first calculate the eigenvalues. For the calculating the eigenvalues, you have to use the perturbation theory in alpha S13. And after that, you can use this formula. Okay. So even this we have calculated, like, people have calculated that exact in alpha and expansion in S13, exact in S13, expansion in alpha. And we have also done with the gamma, same thing. But I have seen that, most transparent for understanding is various effects is this one. For instance, we study something called a magic baseline, where you can see that this term goes to 0, sine A delta by A. So then this CP effect vanishes, and the CP phase gives rise to some uncertainties, and that vanishes. So these two expansions, OMSD and alpha S13, even without decay, are good expansions in terms of understanding the problem physically. That's what I feel. But the calculation is like you have to calculate the eigenvalues in this expansion, and then you have to use a perturbation theory, find the eigenvectors, unperturb, then give the perturbation, calculate the eigenvectors, and then you use the Cayley-Hamilton theorem to get the probability.
So, you said like decay terms can be different ones, but have you really applied a model and looked for this constraint that could come from decay, like a full scale, where you have the interaction, suppose you have a light scalar, and then it can fit the matter potential plus the decay term.
So that we have not done. We have just, for our purpose, we just assume that it decays and we solve the propagation equation. There were earlier some papers by Sandeep Pakwasa and these people, and Anjan Joshipura. They have done some, they consider a Lagrangian, they have a model, and then they tried to do, but I think this was mainly for visible decay. Now, visible decay, the problem is that you have a state, active state, to which it is decaying. So then you have to also consider that, and there is an energy degradation of that state. So people have studied that. I have to really think how for visible decay, maybe our propagation will not change, but on the other hand, the state to which my neutrino is decaying, that is going out of the system. So it is not in my propagation equation, but when it's visible decay, then how that happens, I don't know. I really have to think about it. So we are always saying this is for visible decay, invisible decay, because in here what is happening is the fourth state is decoupled. So it's a sterile state. So I have a 3×3. If it's a visible term, then I have to see it's going there. So that is a little different, but phenomenologically people have done solving numerically visible decay and invisible decay for various experiments, but the analytic expressions were all vacuum expressions, or people just give p alpha beta u to the, but no closed form analytic expressions were given earlier.
So one other thing is, suppose I bring in a sterile.
Yeah, that's what we were trying. So what happens is very interesting because we are doing that, I can tell you. So then we studied the sterile neutrino which is decaying. Then, if you have the sterile neutrino, then in the long baseline experiment, it causes some wiggles. So what my students like Dibbo Chattopadhyay, who is my collaborator in this paper work, he just informed me a few days back that he has done the calculation and he sees that those wiggles are vanishing. So I have not studied the full repercussion, but it's interesting to see if the sterile neutrino is there.
And one convoluted thought in that regard is, can you explain mini moon and not seeing the effect of sterile neutrino in other places using the
Yeah,
it's possible.
I don't know.
Oh,
I have to see the sterile neutrino results, and I told them after we did this, I told them to do, but he was writing his thesis and he was working on some other things, and same as my student. So my student and this Dippo is Amol's student. So they both are now working on that, but like this is the initial result I see, but like it's like a sterile neutrino going to a sterile state. That's what they are doing. So.
Is there any further questions? Okay, if not, the rest of the speaker.
Not from Zoom.